In this part of the tutorial, we'll explain how Graphene securely encrypts and decrypts input and output files of the application inside the SGX enclave. This feature of Graphene is called Protected File System, or Protected Files for short. Graphene implements a feature of protected files in addition to and relying on remote attestation. Since the user application runs on an untrusted machine, all input files as well as produced output files must be at least integrity protected. And if user files contain sensitive information, they must also be encrypted. With the protected file system implemented in Graphene, all required files to run the workload are created by the user on your trusted premises first. The files are then encrypted with a user-provided symmetric key. After that, the files may be shipped to the untrusted machine together with the application binary and Graphene. After the SGX enclave is created, Graphene needs to obtain the user key used to encrypt the files. As explained previously, this key provisioning can be accomplished via secret provisioning with remote attestation. And once the key is securely provisioned inside the enclave, Protected FS subsystem of Graphene uses this key to decrypt the input files and run the workload. After the enclave is finished with a secure computation, the application typically produces an output file. This file is also transparently encrypted by the Protected FS with the same encryption key. Finally, the output file may be moved to the remote user, where it will be decrypted. Graphene implements protected files as transparently encrypted and integrity protected files. The specific files or whole directories to be treated as protected must be specified in the manifest. The encryption format used in the Protected FS implementation is borrowed from the similar feature of Intel SGX SDK. To recap, we would like to remind that in addition to the allowed or completely unprotected files and trusted only integrity protected files, Graphene also supports protected or fully encrypted files. Protected files are encrypted with a user-supplied key in a special format, and this user key must be shipped to the SGX enclave using remote attestation via array-TLS and secret provisioning explained previously. And protected files will be always encrypted as soon as they leave the SGX enclave perimeter. And in our GitHub Graphene repository, we have one example of protected files called array-TLS secret provisioning. This example shows both the provisioning of a secret key after remote attestation and also how the input file is marked as protected and transparently decrypted when the SGX enclave starts. We also have an end-to-end PyTorch tutorial, which shows, among other things, how remote attestation and protected files work with PyTorch, and we encourage you to look at this tutorial. Let me show you an example of secret provisioning and protected files that is shipped together with Graphene. Here I have my SGX enabled machine with Graphene installed, and I will show you the array-TLS secret provisioning example. This example has the server, the secret provisioning server, that waits for SGX enclave clients to connect to it. The server verifies that these are the correct SGX clients and provisions a secret key, which will be used by the SGX client to decrypt the input files. So let me just show how it works. Let me first build all the required files. And we see how embed TLS is built and all the server and clients are also built here. And let me just build additionally the decap versions of all these required libraries. So now we see that we have the secret provisioning server that uses the decap remote attestation of SGX. And we have three different secret provisioning SGX clients. We will use this last one, PF client, which reads the protected file. And we can see that we have the plain file which just contains the hello world string. We also have the rep key, which is just some dummy user-supplied key to encrypt and then decrypt protected files. What we need to do is we need to create the additional input.txt file, which will be encrypted in the Graphene format. So now we have our file's input.txt file, which, as you can see, is encrypted in the format of Graphene protected files. And this file actually contains just the hello world text, which is encrypted with the rep key. Now we can start the secret provisioning server. This secret provisioning server simply waits on a port 4433 and waits for clients to be connected so that it can send the master the rep key of protected files, which was read from file's rep key, to the SGX client. So let's start our protected files client. And we can see that the server received a request from the client. It received the SGX certificate with MR enclave, MR signer of the SGX enclave in which the client runs. And at this point, you as a user in your production environment would like to compare this with the known good values to identify this SGX enclave. But for now, our server simply sends the secret key. This is the rep key in the hex format, so that the client can use this key and decrypt the protected file. And you can see that the client spawned a child process which received the protected file's master key. And using this key, it decrypted the input.txt file and read the hello world string from it. And the same happened with the parent process of this client. So you can see now in this example that the secret provisioning server waited for our SGX enclave client to connect to it, send the SGX certificate. The server checked its MR enclave and MR signer and verified that this is the correct SGX enclave with the correct client application running in it. And so the server provisioned the key for protected files. The client received this key, decrypted the input.txt file with it, and read the expected hello world string from it. And this concludes this part of the tutorial.